So there's really two windows. When you do a sniffer trace, this is what you'll see as the sender's window. So right here, window size value 8192. He's saying, the receiver saying, I can handle up to 8,192 bytes at one time. And then that's the most I'll accept from you, and then I'll send you an acknowledgement. What you don't see here is the person who sent this. So let's say this came from my laptop, okay, and this is what I got back from the server. I know the server can handle this much data at one time. What I don't see in here is, what is my laptop's sending window? What's my congestion window right now? I don't know. It's not part of the sniffer trace. But it's a variable that your transmission control block keeps track of. You know, if things are chugging along nicely and there's no congestion, your send window, your congestion window will probably be pretty large. It might be equal to this number. But if there's congestion, then your laptop will say, well, even though he's telling me he can handle a lot, my congestion window is actually smaller. It's like 4,000 bytes. I've shrunk it. So I can't send this much anymore. I now need to adhere to my send window, my congestion window. So the moral of this story is TCP is keeping track of two windows, the sender's window and the receive window, what the receiver can handle, and the sender's window. And whichever one is smaller, that tells this guy how much he can send. Like, for example, let's say that you're sending a bunch of stuff to me, and from your perspective, everything's great, right? When we very first started out, we both told each other 8192. You told me you can handle 8,192. I told you I could handle 8,192 bytes. Okay? We're chugging along. Now, all of a sudden, when I send you an acknowledgement, you look in the window field of that acknowledgement, all of a sudden it says 3,000 bytes. But your send window is still 8,000 bytes. Well, 3,000 is less than 8,000, so now you know that you need to slow down because I've just shrunk my receive window. I've now told you, don't send me 8,000 bytes anymore, send me 3,000 bytes at the most. Now remember, we don't know how many segments that's going to fit into. That's completely up to you. If you're filling up segments to the maximum segment size, maybe only 2 segments will be it, and then that's it. That'll fill up my receive window. Or if your segments are tiny, tiny little segments with maybe 50 or 100 bytes each, you might end up sending me 9 or 15 segments before you hit my receive window. So this window size value here that we see, it's not counting the quantity of segments, it's counting the quantity of bytes. Now there's one other thing I want to show you. And this particular sniffer trace, I don't see it on here, so I'm going to bring up another one right here. Let's move this out of the way. So this is a sniffer trace of when I actually downloaded a little video from INE, like some of you guys do. You go to download.ine.com and you download whatever you're authorized to download. So here's the TCP three-way handshake, so 10.7.1.101, that's my IP address. So here's the sync, and if I just make this a little bit bigger, come on. Okay, so here's the sync. So in my initial sync, I did the active open, and so in the options field, I set the, come on, where is it? Not the options, over here, the control bits. I set the sync bit saying I would like to synchronize a connection with you. And this very first TCP segment, now here it says sequence number 0. I'm going to give you a little trick here. As I mentioned, the initial sequence number is actually a random number. And we can see, just look at the size of this. When I click on sequence number down here, what's highlighted in blue? 1, 2, 3, 4 bytes. All right, so the sequence number field is actually a 32-bit field. So it could have a potentially huge sequence number. Now this says 0. Is it really 0? No, it's not. This is something that Wireshark is showing us. Notice how it says relative sequence number. It's saying this is the very beginning of the conversation. and I haven't sent you any bytes yet, so 0 bytes. And then the acknowledgement comes back, and the acknowledgement says, okay, the next time you send me something, I expect it to start with sequence number 1. And here I go. Here's my ACK. So there was sync plus ACK. Notice the sync bit and the ACK bit are set. And then here's the final ACK. And here I said, okay, I'm starting with 1. But remember, we don't actually start with 0 or 1. We start out with a random huge number. So why am I not seeing it here? Well, this is just something Wireshark does. It says a relative sequence number. So for example, my ACK, final ACK, 1. Okay, now let's take a look at the first data that I sent. Scroll down here a little bit. So here is my HTTP GET message. You can see it's pretty big, 1,245 bytes. And yet it still says sequence number 1. And it says the next sequence number I'm going to give is 1192. Now why does it say that? Because it says the actual length of this segment, 1245, is including the TCP header and the IP header. It's not just the data. The data itself is right here in TCP segment length. So this is saying, okay, the actual data I'm holding is 1,191 let's see, bytes. I believe that 1,500 bytes? Yeah, bytes, 1,191 bytes of data. So it says the next time I send you something, it's going to start with 1192. You see the way TCP works is every single byte that goes into a segment is sequenced. Let me draw something here just to describe that, because I know this is getting a little complicated. Okay, so let's say during the three-way handshake, I came up with an initial sequence number of 5,000. Okay. Now let's say this is the very first segment that actually has bytes in it. Each one of these squares is going to represent a byte of data. Okay, so inside my mind, inside my transmission control block, I'm going to say, okay, this first byte, I'm going to give that 5001. Second byte, 5002. 5003. 5004. And 5, 6, 7. So this last one would be 5008. So when I send this, when the receiver gets it, okay, he's going to say, okay, I'm acknowledging that. He's going to say, I've counted up your bytes, and I'm expecting byte number 5009 next. So I've gotten everything up to, but not including 5009. But it all starts with whatever the initial sequence number was. If the initial sequence number was 8999, then we'd have 8999, 9000, 9001, 9002. So every single byte is sequenced, and the acknowledgement tells how many of these bytes, hopefully all of them, did the receiver get. So how do we see what that actual initial sequence number is? Well, in Wireshark, here's the little trick you can do. You can go to Edit, Preferences. There it is, Edit Preferences. Click on Protocols. And here's all the protocols Wireshark recognizes. Scroll down to TCP. Here it is, TCP. And I don't know if you can see this well in the video or not, but there's a field right here called Relative Sequence Numbers. It's the 5th field down, and right now it's checked. So if I uncheck that, and then hit Apply and OK, now we'll actually see in my initial sequence, in my initial sync, here's my initial sequence number. Whatever that is, 2,960,359,927. So this is the initial sequence number that I created. And then every single byte of data I send subsequent to that will just make that number climb. So So that's how you see what the actual sequence numbers are. And then the server that I'm talking to, when he sent me his sync, he said, okay, I'm going to start with this one. Another huge number, 2,352,352 blah, 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 blah. So you can see here, these numbers are radically huge. They don't have to be this large. It's just some random number they came up with. So the window sizes we've talked about is saying how many bytes I can handle at one time. Now, there's another reason I brought up this sniffer trace, and now I remember what it was. Okay, so let's take a look at my initial sync. When I was communicating to the server, let's just scroll down here if I can. Right here. I said initial window size 65,535. So let's think about this for a second. So you might look at that and say, okay, so my laptop was telling the server, hey server, when you start downloading that video, that huge, 5 gig file or whatever it is, you can send me up to 65,535 bytes at one time. And my laptop said, if I haven't acknowledged you by that point, you need to pause and wait. And then when I acknowledge it, you can send me more. So the way the server sees this is the server says, at any given time, the most amount of bytes I can have out there in the air that have been unacknowledged is 65,535 bytes. That's the most. But here's what I want to show you. Look at this thing here, window scale. Now window scale is something that is it's optional. It doesn't have to be in there. And if you're the type of person like me who likes to know RFC numbers so you can look this stuff up, it was originally implemented in RFC 1072, that's 1072, and then it was updated by RFC 1323. So what is this? Let's talk about what window scale is. And let's bring it down to some more reasonable numbers. Let's say that when I sent you my initial sync, I said my window size was, let's make it easy, 128 bytes. Of course, it's tiny, but let's just use that as an example. Okay, so the actual window field, if I go back to it here, window size right here, let's look at down here in blue. FFFF. So notice that's 2 bytes. Right? So the window size field is 16 bits long, 2 bytes, 16 bits. So if I have 16 bits, what is in binary, what is the largest possible number I can come up with 16 bits? Actually, it's what we saw right here, right? 65,535. If I have 16 bits all set to ones, that's 65,535. But wait a second. What if my laptop or the server actually had the capability of buffering even more than that? What if I wanted to tell the server, hey, you can actually send me 80,000 bytes at a time or 200,000 bytes at a time? How would I do that if I only had a 16-bit field to work with? This is where that window scale comes into play. All right, so let's take a look here. So here's my window, 16 bits, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's my window. And right now, I've said you can send me up to 128 bits. So that's 1, 2, 3, 4, 5, 6, 7, right there. I've set that bit to a 1, and everything else is turned off, and everything in front of it. Okay, so if I say in my options, window scale equals 3. Make sure I'm doing this correctly. No. Window scale equals 8. then what this is doing, let me make sure I'm getting this right. 16 bits to the left, scale factor 256. Yes. So what this is doing is, let's think about this here in binary. If I start from the right, how many bits do I have to move over before I set the 8-bit? Right? 1, 2, 4. The 8-bit's right here. So let's put the 8-bit down there. Okay. So the 8-bit is 1, 2, 3. It's the 4th bit over. So if I say Windows scale 8, I'm sending you this number, 0, 0, 0, 0, 1, 0, 0, 0. And basically what I'm telling you is, take this number here and pretend that you had a 32-bit field and shift this number over 4 bits to the left. Windows scale 8 says, right here, I've set this to a 1. That means shift the initial window size I gave you 1, 2, 3, 4 bits to the left. So basically just add, I'll just use a different color here, add 4 zeros to the end of this. And that is now what my real window size is. Even though I could only tell you 128, now what's that number? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. So by having the combination of a window size of 128 and a scale of 8, I'm really telling you my window is equal to, what I say, 2048 bytes. So let's look at how this actually plays out in my Wireshark sniffer trace. In this case, I said that my window size was 65,535 and the scale was 1. So basically I'm taking this value, 65,535, which looks like this. Let's make this a little bit bigger. So that is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 65,535. And by doing a window scale of 1 in binary, so I'm now telling you this. And by the way, look at the window scale. If I click on that, that is a 3-byte field, right? So that's 24 bits. So here's my window scale. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is my window scale in my options field, which is a 24-bit field. And in my particular case, I set this bit, 1. So that said, take this number here and bit shift it 1 bit to the left. In other words, add a 0 right here. So instead of 65,535, that now ends up being whatever that is, 130,000 something, whatever it is. So basically I've doubled it. And I think it actually tells you, does it tell it you right here, window size 65,535? No, unfortunately, Wireshark does not interpret that for you. But take a look at the server. Look at the server. So here is the server. He gave me a window size of, when he was communicating with me, he said window size 17,922, window scale of 8. So let's try to figure this out. Window size of 17,922. All right, so let's bring up my calculator here. So in decimal, 17,922. What is that in binary? All right, so that is that. Okay, so we'll put this right next to it. So the original window size that the server advertised to me was 1, 1, 2, 3, 1, 1, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 1, 0. And that equaled, what was that number in Wireshark? 17,922. But then he also included a window scale, which was 8. Bit shifted 8. So now what we have to do is we have to take that number, 1, 1, 2, 3, 1, 1, 1, 2, 3, 4, 5, 6, 7, 1, 0, and we have to add 8 zeros to it. 1, 2, 3, 4, 5, 6, 7, 8. And whatever that number is, if we were to convert it back into decimal, that's what the true receive window size is of the server. So you can see that server is basically telling me I can handle gobs of bytes. I don't even know what that number is, probably hundreds of thousands of bytes, maybe. But that's how you combine the window with the window scale. You take your initial window size value, and then if your window scale says 8 or 4 or 3 or 2, you basically just take that number, convert it into binary, shift it 4 bits to the left, 3 bits to the left, 8 bits to the left, whatever this says, reconvert it back into decimal, and that's what the true window size is that that device is advertising to you. And someone's asking, how did Windows scale 8 become 4 bits? So in this case, Windows scale of 8, so the actual, let's see here, number is 0308, right, in hex? Actually, no, it's 030308. So in hexadecimal, it was 030308. So in binary, that's 111, 111, and then 8. Wait. 0, 0, 1, 1, so that's hex. 0, 0, 1, 1, 0, 0, 1, 1, so that's 3, and then 1, 0, 0, 0. So that's 3, 3, 8. Let's just open this up here. Windows scale 3, shift count 8. So the first 3 is that. Oh, okay, I see. It's type length value. So basically this is saying in this option, the number 3 indicates this is the Windows scale option. Because all these options have a type, the length of the option, and then what the option actually value is. So this is saying in this particular TCP option, the number 3 is the Windows scale option. The length of this particular value I'm about to give you is 3 bytes or 3 bits, and it says, and now here is the value of 8. Okay, so the actual Windows scale is 8, so type, length, and actual value. So if we take 8, 128, 64, 32, 16, 8, 4, 2, 1. Okay, so that right there says bit shift 1, 2, 3, 4 bits to the left. All right, so I did a little bit wrong. It shouldn't be, I did too many of them. So 1, 2, 3, 4. That's what you would have. So if this original thing was 17,922, we're adding 4 zeros to it because the number 8 is in the 4th binary place. And so now whatever this resulting number is, that's what the correct Windows scale is. Shift count 8. Oh, okay. Shift count 8. This is actually telling us, this isn't actually the number in binary. This is saying, it's actually explicitly saying move everything 8 bytes to the left. So my original thing was right. Let's just put some of this in here just to clarify it. So option TCP option type. I'll just say the name of the option. TCP option length. And this is TCP option value. So with the window scale option, this last number here says how many bits to the left should you shift the original window that I gave you. So this right here is saying add 8 zeros to the end of this number in binary. Basically the way that turns out is 1, 2, 3, 4, 5, 6, 7, 8. And that number right there, hold on a second. 1, 2, 3, 4, 5, 6, 7, 8. So that number is 256. It's saying add 8 zeros, and then where this 1 is, that's where you should start your number. So add 8 zeros. And this number here in decimal is the number 256. So it's saying place your 1 in the, basically 8 zeros, and then the 1 goes right here. So 8 zeros after this number. Do we have another one here I can show? I think this is always the same. So like in my case, clearly I could not handle as much. So my initial window size was 65,535. Where is that? Right there. And then when I was talking to the server, I said, just shift it 1. Just add a single 0 to the end of this number, which is basically doubling it, right? Multiplier of 2. TCP implementations don't have to use this option, this window scale option. If a device decides, hey, 16 bits is plenty for me to advertise how many bytes I'm willing to hold, it doesn't have to include this option. But it looks pretty clear here that a lot of applications these days say, hey, look, I can handle a lot more bytes than 65,535 bytes. And so in order to advertise that, we have to combine the window value with the shift count. And yes, in the live stream, Oliver has a point here. He says he thinks it's the window size, which is this, times 2 times this. Yeah, so if this number was 3, 2 times 3 is 8, so you'd have 8 times the window size. If this number here was 4, it's 2 times 3 would be 6. And I'm getting a little overly complex here, but basically the way I think about this is I say, okay, this is designated the number of zeros I have to have after this. So whatever the number this is, if I convert this into binary, if the shift count here says 7 or 6 or 5, that's the number of zeros I add after this. And then that'll give me my final number, my final window size. Okay, so we'll see coming up when we talk about sliding windows, how this window can actually grow and shrink during the course of a connection, and what can cause that to happen, and how these ideas of a receive window and a send window are maintained by the transmission control block in the TCP operation of your particular device.